Today we're going to look at the top coder challenge for the min heap challenge. I've gone ahead and built out this min heap. The first thing we'll take a look at is the node. So here on the right you can see my node class. As you can see, I've extended the node just a little bit. I've added an ID to the node. This is to allow it to keep place in the tree as we're building it. And then I've also added a toString method to the node, and that's to print out the values in the node as requested per the challenge. Alright, so go ahead and close that down now, and we're going to take a look at our min heap. Let's go ahead and run the rspec just to show you that the rspec itself works. Using the bundle exec rspec command at the console or at the terminal, go ahead and run it, and as you can see it passes all the tests, 0 failures, and all 7 examples are green. Okay, so going in to take a look at this, I'm just going to clean this up just a little bit. Some things I didn't use as I was building out this code. So I'm building out the min heap, and the min heap has an adder reader for both the root and count values. It initializes when you pass a value in. This is going to be a node at some point. It's going to initialize the root node with the root value passed in. I'm giving this node a value. Let's go ahead and open that node up real fast one more time just to take a look. You'll notice that the ID when you build the node is initialized at nil. Again, this ID value is being used to tell the heap where the node is in the heap. And then the count here will tell us the size of our heap if we needed to check that. It's also used to actually update the ID value as we can see when we insert the nodes. So the insert, it's going to take a value, the root value, and this is where it's starting the search for the parent value for the new node. It's going to when the new node is inserted, it's going to give that new node an ID, and this is going to be the count value plus 1. Remember, the count value starts at 1. This is where the root value is, and it's going to give the new node that ID, and at the end of the insert it actually increments the count value by 1. Again, we can use the count value to get the size of the heap. Then it's going to find the current node in the location. Now this is the parent node where the new node will be attached, and it checks the parent node to see if the left value is nil. Again, it has to completely fill each tier, each level of the tree from left to right. So it checks the leftmost value of the current node. If nothing is there, it adds the new node there, and if something is there, it adds the new node to the right-hand value. Again, this is a binary tree, so each node only has 2 pointers to new nodes. And then after it sets the new node to whichever branch of the current value, it adds a pointer back to the parent of the new node to the current value. And then it's going to heapify this node, and we'll talk about heapify in a minute, but basically it's going to sort the node to where it's supposed to be in the heap. I've also created this find method, and the find method, as per the spec, will actually look for a node in the heap by its rating. So rather than an ID in the node, it's just going to test the rating to make sure that the node exists, and if it does, it gives that node back to the user. So again, it's starting at the root value, and that's the top of the tree. It's going to return the root if the root rating equals the data that's passed in. That's not in any of the built-in tests, but it will actually pass back the root rating. So it does search every node in the heap. Then it proceeds to recursively search down the left side of the tree, and it will return that node at the end of that tree. So again, it's recursive, so every time it finds a nil value, it will actually find root left, so it just keeps checking the left-hand nodes until it finds the value. If it doesn't find if it doesn't find the node, it passes it on to this left tree value, which recursively runs it back through the table. Once it gets to the nil, or to the very end of that tree or that branch, it then runs the same thing on the right hand nodes, basically until it gets to the end. If it finds it, it returns the node up here, return root, if the root.rating is data. Again, that root value there, poorly named attribute at the top, but it's a good pointer to show that it starts at the root value. It's going to return that value that's passed, or that node that's passed in, by checking the data. If it doesn't find it on either side of the tree, it returns nil. The next one is actually the print method. If you remember, I built the toString method into the node. So what this is going to do is it's going to create a queue using the built-in queue class in Ruby. Then it's going to enqueue the root value. Okay, now this is important. Remember that root node has 2 pointers to the left and right child. Okay, and then it's going to run through the queue, and it's going to start to empty the queue. It dequeues that value, which is currently root, into the variable value. Then it's going to put the value, which is going to be that node toString method, because each of these values is a node, unless that value is nil, unless that value title is nil. As it does that, it's going to enqueue the values that are found at the left and right pointers of each node, which then adds those into the queue. And if we remember the queue, it's first in, first out, so it adds the left value first and then the right value. So when it dequeues, it will also dequeue the left value first and then the right value. And as it dequeues that left value, it will check the left and right nodes, and so on and so forth, until the entire queue has been printed out. Then we have our delete method. Again, this is just a simple delete method. It uses the find method from above to find the target node that we're trying to delete. If it doesn't find, or if the data that's passed in is nil, it's going to return nil. If it doesn't find the target, it's also going to return nil. Then what's going to happen is it's going to find the last node in the tree. It's going to if the target is the last node in the tree, it's going to remove that last node, and we'll go down and see that in a minute. And if it's not the last node, it's going to run this remove method. Okay, so the remove, or I've added some private methods, and these are just going to be the methods that are helper methods for those above. The first one that I have in here is the find parent method. So remember, we have to find the parent method during the insert in order to add the current node, or in order to add the children to the current node. It's going to return the root if the root ID is equal to the data ID divided by 2. Again, every parent node will be exactly 1/2 of its children, and this is a floor divide by 2. So for example, node 3 divided by 2 returns node 1, which is essentially the root. Again, it's going to basically run through that find recursion until it finds it. If it doesn't, it checks the other side of the tree. If it still doesn't find a parent, then it returns nil. The next method we're going to talk about is the heapify method. Now what this method does is it bubbles up each of the newly inserted nodes basically until it finds its proper sorted location in the tree. So the node that's being passed in, remember when we insert a node, it has a parent value set in, so it checks the parent, or it sets this parent variable to that parent node, and then it sets the left and right child to the parent's left and right, because again we're bubbling up, so we're checking each child against the parent. If the child is smaller, it's going to bubble up that child. So until the node rating is greater than the parent rating, if the left child and right child does not include nil, it's going to test the children against the parent rating. If the left child is greater than the right, or then after it does that, it has to check to see which child is less, because that's the bubble down value. So the parent, if it's greater than any of its children, it finds the least of those two children and then bubbles the parent down and the child up into that lesser child value. When it does that, it's going to use the swap method, which is just a helper method for this heapify. And the swap method's right here. It's just going to take the parent rating and the child rating, and it's going to swap them, and the parent title and the child title, and swap it. So essentially those nodes are like memory locations for values in the tree, and when it finds those values, it swaps those location, or those values at those locations. So the structure itself is maintained throughout this this build. After it swaps the children, it reheapifies the parent. Again, this is to make sure and maintain that every root for every branch is the smallest node in that particular branch. Again, we have our remove methods. Remember, if the node is being deleted is not the last child in the tree, it has to run this remove helper method. And this remove helper method sets a last node value to the last node in the tree, and it does the find last, which is lower down in the helper methods, and it's going to find last against the root and the count, because again the root value is where we insert into the tree, and the count will always be the very last node in the tree. And that's kind of like our find data methods as well. And that will be the ID of the last value in the tree. Then we are going to run swap nodes against the target that we're passing in and the last node. So again, we're using that swap node method, so we're swapping the values of the rating and the title. Then after we do that, we remove the last node, because now our target node to be removed is the last node, and we know that method works from up above. And then we want to down heap the target. Again, the reason that the last node is the last node is because it has the largest rating value, which means that it will be greater than all the other values in either of the children branches. So we need to bubble that down to the correct side and location of that tree. And that's what this down heap method does right below it. So again, it's basically doing essentially the same thing as the heapify, it's just going in the other direction. All right. So I'm setting down. In this down method, it returns if target left and right are nil. And again, it's checking that all. And somebody told me that I should probably set a proc there, so go ahead and do that. With Ruby 1.5, it actually allows me to do the all just on that value, but with lesser Rubies, I actually have to set that as a proc. Then down equals, so I'm setting down to the smallest child of the parent node, of the target node, I should say. Again, the target node is that value that's being transferred with the last node. So the last node is that target value. The last values are that target value. And it has to bubble down onto the correct side of the tree. So it's going to find the smallest child, again, just like we did with the heapify. And if there are no children, or if there's no child to the target left, then it sets that target right to down. And if it is a target left, then it sets the target left to down. Then it swaps the nodes with the target and the down. If target rating is less than down rating, and then it down heaps again to keep this process going until the target node is in its proper location. The find last method, again, this is just used to find the very last node in the heap. Find smallest child. Again, you're testing values against the left and right children. If the left is lesser, it returns the left. If the right is lesser, it returns the right. And then that remove last node. So what it's doing is when it removes that last node, it finds the parent of the last node. If parent right equals target, then it's going to set the parent right to nil, so essentially removing that pointer. If left is the target, it does the same thing. Then it reduces the count by 1 because at this point our heap has grown 1 less. And so when we want to insert a new node, we have to insert it at the new count, which is where it should be. Okay, so let's go ahead and test these out. Again, we've already run the RSpec, and having done that, then we can just go ahead and see each of the tests from the RSpec in the console here, so we don't just get a cryptic, hey, you passed sort of idea. So let me go ahead and clear the console, and let's uncomment the insert test. Again, this is just inserting nodes along the way. As it does, you will see that it heaps them properly. Now, if we take a look at the nodes, node 4 is Donnie Darko at 85. Node 5 is Inception at 86. Node 6 is District 9 at 90. And node 2 is Braveheart at 78. Now, you'll notice that 4, 5, and 6 are in sorted order. So when they insert into the heap, they'll actually insert in sorted order. But when we add node 2 is the smallest node of that group. So it's going to have to bubble up, and the others are going to have to bubble down. Remember, when we add our root values are node 0 value, and that's the matrix at 87. So already it is greater than several of these nodes that bubble in. So if we want to see this in action, let's go ahead and actually print this out to make sure that these are inserting. So we'll save it, and we will run the program itself. I forgot I had a print at the bottom as well. So let's clear this out one more time and run it one more time. Okay, so you'll notice that Braveheart, the smallest node in the heap, has bubbled all the way to the top. It's the first node printed out, which as per our print method shows that. It's the first method to come out of the queue, or first node to come out of the queue. So it prints Braveheart at 78. Then to the left of that is Donnie Darko at 85, and to the right of 78 is Inception at 86. Then we switch levels, and so level 2, its first parent is 85, because that's on the left, and 90 is going to be the node to the left, and 87 is the node to the right. So as we can see, it follows the sorted order for our min heap. The next one is it's doing that insertion test, and I should note that the insertion tests are labeled with right and left children. So it's actually finding, and as I'm explaining it, if you want to follow along while I'm explaining it, you'll notice that this next one will be at the right-left child. Okay, so the next nodes passed in are 9, 8, 2, 5, and 11. So if we look at 9, it's District 9 at 90. I'm sorry, 9 is at Star Wars A New Hope at 93. 8 is The Martian at 92. 2 again is going to be the Braveheart at 78. 5 is Inception at 86, and 11 is Mad Max 2 at 98. So let's go ahead and print this out. So clear screen and print it out, and we'll walk you through the tree. So again, Braveheart, which is the smallest node, is bubbled all the way to the top. Donnie Darko is node 85, so it's the left node of 78. Inception is the right node. Let's do that one more time, just to make sure. Oh, I knew I was looking at the wrong values. Okay, so again, Braveheart is 78. 86 is Inception, so that's going to be the left node of 78. The Martian at 92 is going to be the right node of 78. Our next level starts at 86. So the left of 86, or the left node of Inception, will be Star Wars A New Hope at 93. And the right node is at 87. So that left branch is full now, so we move to the right branch. Again, that right branch starts at 92. It's the right of 78. So 92, its first node will be 98, which again is greater than 92 in its left branch. So that is the right-left child. Okay, our next test is the find test. So again, I'm inserting nodes 2, 4, 5, and 6, and I'm looking for the node on the left, right. And so we're going to pass we're going to put the return of the find heap, and I've modified this string a little bit to show you that the title and the rating of this found node is what it should be. So again, I'm inserting node 2, 4, 5, and 6, and then I'm going to search for node 6, and I'm going to return the title there, and again, searching for node 6, I'm going to return the rating here. So let's go ahead and do that real fast. And remember, node 6 is district 9 at 90. So save the uncomment, clear the screen, and run again. And notice that after I've run it, it has found district 9 at 90. Okay, again, finding the right-left node, I've inserted the 5 nodes, 2, 5, 11, 9, and 8. Then it's going to look for node 8 and return the title and the rating. And I do get that these lines are a little bit long here. According to the best coding practices for Ruby, but I wanted to make sure that it was very, very clear what was being printed out. So this is just for the test itself. So go ahead and save that and clear the screen again and run the program. And again, we were looking for node 8. And if we check our node 8, it is the Martian at value 92, which is what is returned. Okay, then we have the delete test. Now, let's go ahead and again, our first test is going to those same 4 nodes, 6, 2, 4, and 5. We're going to delete node 5 from this tree, and then we're going to print the value that we find at node 5. And the reason we're printing it with just the p here is so that we can actually see that it's returning nil. And then I'm going to go ahead and print out the remainder of the tree. So clear screen, run the program. Must have not saved it. Run the program, and as you can see, it does indeed return nil when it finds nil, and it returns 4 nodes. Remember, we have 5 nodes total in the heap after the insert because of the root node, and then it returns the 4 that are remaining in heaped order. Okay, our next test is to delete the right-left node. So again, we're inserting those 5 nodes, 9, 8, 2, 5, and 11. We're deleting node 11. We're going to run the same find method, and then we're going to print the heap. As you can see, it does return nil here, and it returns 1, 2, 3, 4, 5. Remember, there's 6 nodes, including the root, so one of them has been deleted, and it is node 11, which was Mad Max 2, the Road Warrior. Notice Mad Max 2, the Road Warrior is not in our final heap. Okay, and then the print test for the final print, and we'll actually walk through this tree, is going to be, we're going to add almost all the nodes. I think 4 is not added in for whatever reason, but we can go ahead and add that in if we really need to. But again, we're just printing the tree, and we'll go ahead and walk down that tree. So let me make this a little bit bigger so that we can actually see it when it's printed. Okay, so notice it prints 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12, including 2, 4, 6, 8, 10, 11. Sorry, 11, including that root value that was passed in at the beginning. You'll notice that it is in heap order, so Pacific Rim, the smallest value, 72, is at the root. To the left of that is 78. To the right of that is 80. Our next level starts at 78, so the left is 87 and 90, which fit the sort order. Then we have to go to the right value of the root, which is 80, and those left and right values are 94 and 86, so again, fits the sort order. Then we jump back to, let's see, left, right, left, okay, 87. So 87's left value is going to be Star Wars: A New Hope 93, and right value is 91, which fits. And then our right value there is 90, and The Martian at 92 and 98. Again, we have followed the sort order.